Hello, and welcome to the Toxic Comment Classification presentation to fulfill the Capstone requirements for PREDICT-498, Section 56 during the winter 2018 term. This presentation is the culmination of the Masters of Science in Predictive Analytics program at Northwestern University and will cover a real-world business problem as well as its solution through the use of advanced predictive analytics. I'd like to start off with a brief introduction to our team, our roles and responsibilities, as well as our company's core values as they inform our approach to solving real-world problems with innovative, forward-looking solutions. Team 4 Green is a small predictive analytics company with a mix of talents and expertise in the field of predictive analytics. We have a shared passion for improving people's experiences online and bringing the humanity back into digital interactions. We specialize in the use of advanced text analytics to empower companies to create safe environments and forums where they can be assured that all of their users' views and ideas are respected and shared with one another in a mutually respectful manner. While our team has specific job titles and unique specializations, we approach all of our projects in an agile manner and work cross-functionally to ensure our clients' needs are fully met. Analytics modeling is overseen by David Law, programming languages by Joseph Ellis, report writing by Luis Messin, and Ricardo Herrera bridges our three work streams as the head of communications and engagement. While some larger companies are bogged down in rigid structures and still use a standard waterfall approach to their projects, at Team 4 Green, we believe in dynamic solutions and understand that over the course of our project engagement, our clients' needs may evolve. Our response to this need is approaching each of our projects through the use of the Agile method. The Agile method is recursive in its approach, which allows for a continuous feedback loop with our clients, maximizes utility through incremental gains, and is dynamic enough to accommodate changing business requirements. We currently follow a CRISP-DM methodology consisting of 6 components. Those components are business understanding, data preparation, modeling, evaluation, and finally deployment. As you'll note, business understanding and data understanding are 2 recursive components of the Agile method, as well as data preparation and modeling. What this means for our client is that during each of these stages, we're constantly learning, growing, and adapting. Evaluation and business understanding is another recursive component, finally followed by deployment. At Team 4 Green, we recognize and understand the ever-growing need to manage digital interactions, as well as the unique challenges our clients face in doing so. According to a survey of over 4,000 U.S. adults by the Pew Research Center, approximately 41% of Americans have been personally subjected to harassing behavior online. Similarly, a study conducted by Data and Society with the Center for Innovative Public Health Research found that 36% of Internet users experience direct forms of harassment. The inability of major social media companies to respond to this issue through traditional methodologies, including user-driven flagging, has been recognized, and it's our belief at Team 4 Green that the only effective and non-cost prohibitive solution to this problem is the deployment of machine learning techniques to proactively identify this type of behavior, and others are beginning to come to this realization as well. On March 31st, 2017, Twitter's Vice President of Engineering Ed Ho stated the following: "This week we're introducing additional updates that leverage our technology to reduce abusive content, give you more tools to control your experience, and communicate more clearly about actions we take. We aim to only act on accounts when we're confident, based on our algorithms, that their behavior is abusive. Since these tools are new, we will sometimes make mistakes, but know that we are actively working to improve and iterate on them every day." At Team 4 Green, we recognize the business problem and have broken it down into what we believe to be the current situation, the relating complications, and most importantly, the solution. The current situation is that while online discussions are definitely a great way for companies to engage their user base and build communities, they're often plagued by users who harass others with toxic comments. This type of harassment leads to reduced engagement when toxic comments are allowed to proliferate. The complication to this is that moderation of conversations via human monitoring is costly and limited, especially when you consider that conversations are occurring at such a high volume and velocity. On average, it would take nearly 30,000 moderators inspecting 12 comments a minute to review the number of messages posted to Twitter every single minute. At Team 4 Green, we believe the resolution to this is an analytical solution which can autonomously identify threats of abuse and harassment in online comments by analyzing patterns and keywords. The solution seeks patterns in text that are indicative of toxicity, such as the use of profanity or excessive punctuation. Identifying these comments in a timely fashion allows companies to better enforce civil dialogue and cultivates a better online experience for its customers. Team 4 Green is excited to announce our partnership with Conversation AI. Conversation AI, a research initiative founded by Jigsaw and Google, is currently working on tools to improve online conversations. Due to the complexities of text analytics and their need to identify toxic comments, Conversation AI has contracted the expertise of Team 4 Green to build an analytical tool with this capability. Their specifications are that we must use Python programming to implement data analysis. The hardware and software must pass the IT architect review. The dashboard must be accessible 24 hours a day, 7 days a week, and have a short response time. The dashboard must be accessible from any authorized mobile device, and the platform must adhere to corporate security policies for sensitive data. At Team 4 Green, we like to level set client expectations by going over what we believe to be the project constraints, as well as what our assumptions are. The project constraints are that the acquisition of new data and its required labeling for classification could delay the project beyond the 10-week deliverable period. The data types and structures provided to the final dashboard will be limited to those in a Wikipedia comment corpus. And finally, the dashboard will display the following metrics: a toxicity index, a word cloud of toxic keywords or phrases, a toxicity classification and clustering maps, and that interfacing of the dashboard platform is not necessary and thus will not be included. The assumptions that we're working under are that the scope of the analytical project will not change, that the project plan is ultimately approved, that human labeling of toxic behavior is consistent and universal, that the data pipelines, technology stack, and other resources required to build a complete analytical solution will be available within the budget constraints, that the corpus does not include adversarial examples targeted at bypassing automated moderation, and finally, that the data is limited to the English language. In order to ensure that all of our projects are efficiently managed, at Team 4 Green, we use professional project management software known as MindView 6. I'd like to quickly go over the 5 core phases of the project plan for the Conversation AI engagement, as well as what we believe to be the anticipated cost. Phase 1 will be the project scoping phase, with the final deliverable being the completion of a project plan and an analysis plan. Phase 2 will be the completion of project scoping, with the final deliverable being solutions development and implementation report. Phase 3 will be data quality auditing, cleansing, organizing, and exploratory data analysis. Phase 4 will be modeling, and finally, Phase 5 will be the completion of all project deliverables, including deployment of the requested analytical dashboard. We anticipate that this engagement is going to begin on January 8th with a stop date of March 16th. That total time will be 50 working days, and we're planning to assign 4 analysts There will be a total of 200 billable hours at a combined hourly rate of $500, and this comes to a total project estimate of $100,000 to complete the requested deliverable.
To address these business problems, we first identified several research questions that would guide our solution development methodology. The first question was if we could improve bad customer behavior by better enforcing the organization's harassment policies. An analytical solution that can, directly or indirectly, improve behavior would be greatly beneficial to the customer. And if we can improve bad behavior through enforcement, then can we improve this process using a solution that identifies toxicity? Next, if we were to identify toxic comments, is this definition consistent? Are there keywords or lexical patterns that are predictive of toxic comments? If there are different classes of toxicity, how do they compare in terms of impact and detectability? On the implementation side, we also asked how this analytical solution could be used to most effectively reduce online harassment. How can we also design the solution to maximize customer buy-in? What metrics can we define to demonstrate the effectiveness of our solution? With these questions in mind, we utilize design thinking and issue tree methodologies to map out the problem space. The root issue of the business problem is an online toxicity. From this core issue, we identified four main causes of rampant online toxicity: varying definitions of toxicity, lack of moderation resources, ease of online engagement, and the general attitude of users. We further branched out these issues into more detail. The first cause is that there are many varying definitions of toxicity. For example, a phrase that might be considered offensive to one person might be acceptable to another. Also, racial slurs and obscene remarks may be seen as more negatively impactful than an insult. The lack of a universal definition of toxicity makes it harder to detect toxicity and also makes it more difficult to enforce harassment policies fairly. The second main cause is the ease of online engagement. Users are able to easily engage others without exerting a lot of effort, which encourages those who would otherwise be deterred from being toxic. This may be due to several reasons. The lack of a strong review process for submitted comments means that users can post potentially offensive content without approval. This may exacerbate situations when the harassment policy is unclear and there is no review process to provide feedback to the user. A second reason is anonymity in online communications. While many online platforms attempt to tie users to their real identities, it is far too easy for users to create new identities online. This means that users do not have to be concerned about what they are saying, as it is most likely it will not affect their social standing and reputation. A third reason is the lack of consequences for online toxicity. While users may be banned from the online platform, they can easily create new accounts to rejoin the platform. Even when their real-life identity is known, these users cannot be punished for their poor treatment of other users. This leads to a situation where online harassment is low risk, high reward for these users, so they have little incentive to change their behavior. The third main cause is the lack of moderation resources which can sufficiently enforce harassment policies on online platforms. Due to the extremely high volume of data, it is difficult or even impossible to acquire adequate resources and infrastructure to enforce these harassment policies. The high variance in content, which includes text, images, and video, compounded with the uncertainty in a universal definition of toxicity, makes enforcement a time-consuming procedure for human moderators. Human moderators are also expensive to support, as each staff member has to be paid a salary. Even with a large team of moderators, there is a limited window of monitoring hours that can be supported, which means that abusive users can wait until moderators are offline. The last main cause is the fundamental attitude and behavior of users. While social, cultural, and psychological cause and effects are beyond our area of expertise, we hypothesize that these users feel that their behavior is acceptable due to a general lack of respect for other people and due to the dehumanization and lack of personal connection in online communications. With this issue tree mapped out, we strive to design an analytical solution that addresses as many of these causes as possible by following these concepts. First, the solution should involve the definition of one or more unbiased metrics for identifying toxicity, such that the toxicity of two separate comments can be compared. This allows us to rate and score toxic comments and define response plans based on its toxicity index. Second, the solution should provide methods to increase the barriers to engagement, such as flagging comments which pass a certain toxicity threshold for review and approval. Third, the solution should be automated and require minimal human intervention in the detection and classification of toxic comments. And fourth, the solution should provide methods to reinforce positive behavior. Based on these requirements, we designed our proposed analytical solution to include predictive models to identify and classify toxic comments in up to 6 predefined categories, including toxic, severely toxic, obscene, threat, identity hate, and insult. Definition of a toxicity metric that allows us to compare toxicity levels of different comments. A summary dashboard that shows several metrics, including the toxicity metric, engagement statistics, and highlights of flagged comments, which enables moderators to identify potential issues and high-value targets at a glance. And recommendation for preventative and remedial applications of the labeling system for future work. The details on the implemented solution will be presented after the explanation of our data, methodology, and results.
In order to create a standard pre-processing pipeline, a full data quality analysis must be completed for each text corpus. First and foremost, we must be aligned on the data format for handoff. This includes specification of the file type, such as comma-space delimited text. The text encoding should be either ASCII or UTF-8, and the data should be able to be parsed. Data parsing includes our ability to properly substring, handle delimiters, and compress erroneous data. Also, we should have the ability for the data to be corrected for the semantic parts of the English language. This is called part-of-speech tagging, and there are several English-based tag sets available to complete this process. Data quality is of utmost importance. We must check the data for completeness by checking that the number of observations in the dataset submitted against the number of observations that are used for analytic modeling. We should know if the data provided was segmented in any way that would degrade the predictive ability of the model. And we should understand the sampling methodology so we can correct for any sampling bias. If sampling bias exists, we must weight the dataset appropriately in a statistically rigorous manner. A variable list and data dictionary are provided. This includes an ID variable, which is a unique identifier for each observation, and comment text variable, which is a text string. The training data also contains 6 labels of toxic, severe toxic, obscene, threat, insult, and identity hate. The classification is a multi-label, which means that any particular comment may belong to multiple target classes. Also provided is a sample from the training data below. Data visualizations are immensely helpful throughout the data understanding process. These visualizations allow us to quickly infer whether the qualities and quantities of the variables in the data match what is expected. Histograms and box plots, for example, display the frequency and distributions for a range of quantitative variables. The histograms of comment length and log comment length above are able to show a quick overview of the comment text length in the corpus and allow us to infer that it is log normally distributed. The box plot shown below splits the quantitative distributions by qualitative variables. In this case, we can see the relationship between comment length and toxicity label. Bar charts display quantitative values by category. For data preparation purposes, this is useful to determine the term frequency inverse document frequency relationship of various words in the corpus. Here, we display some term frequencies in class labels of obscene, severe toxic, and threat, and can tell there are strong relationships for certain unmentionable words. Word clouds and heat maps also provide information about the frequency of features in the dataset. Word clouds show the frequency of individual words in the text. We've provided an example of the clean word cloud. Since the training data was provided by Wikipedia, words related to encyclopedia articles, pages, and overall reference materials jump to the forefront. Heat maps show the frequency of qualitative features in relation to each other. In this case, we display the frequency of the various class labels in relation to each other, and can notice that comments labeled insult have a higher than 50% chance to also be obscene. To prepare the dataset for analysis, we must first deconstruct the text string into a vector constructed of each word in the text. This is called a term vector in the vector space model. If we split a comment text into features that contain one word or groups of words, we end up with a very large and sparse data matrix. Variable reduction is helpful to extract meaning and relationships out of this sparse matrix. First, we can remove stop words. These are term vectors that do not contribute to the meaning of a phrase, such as a, an, or the. The meaningful terms can then be analyzed by transforming the term vector to frequency counts of each term. This frequency term can be reduced by removal of low importance terms. To do this, we use metrics such as term frequency inverse document frequency, or t-stochastic neighbor embedding, or t-SNE.
Here are some plots generated using t-stochastic neighbor embedding, which show the top 10,000 unigrams ranked by TF-IDF score that were extracted from our training dataset. The 6 plots, from left to right, top to bottom, are for the 6 toxic categories of toxic, severely toxic, obscene, threat, insult, and identity hate. We can observe from these plots that comments tagged as generally toxic are densely clustered as shown in the top left portion of each graph. This confirms our hypothesis that there are certain terms that are highly predictive of toxicity. We can also see that the toxic and insult categories are more widely distributed in comparison to identity hate, which implies that these categories have more dependence on semantic context than keywords as one would expect.
Hi guys, welcome to our few slides that we have here on our text modeling process. I kind of want to just take these slides to do a really high level walkthrough of how we think about modeling text and social media comments for toxicity. So from the start, our goal was to model our data into levels of toxicity. And to that end, we have kind of 6 levels of toxicity classes. And we're looking to try to take raw text values or unstructured text and forecast kind of a 0 or 1 outcome for those toxicity levels. And that kind of to that end, we chose 2 classes of models to kind of work with. One is a more linear model or a logistic regression model. One is kind of has a lot more degrees of freedom, which is the RNN. For each model, we kind of wanted to separate out our training, validation, and test data. So kind of in the age of bigger data, where we have kind of lots of observations and we're trying to avoid overfitting, we really want to have a training set, a validation set, and a test set. Where the test set is functioning as it's kind of holdout data. Our model has never seen that data, and we can use that as a kind of test for our efforts within the training and validation sets. So we can see here the data is kind of represented here for each model. For the neural network, we have kind of 90% of the data in the blue bar and a 5% validation set that it's being fit to. And given the nature of it, that's kind of more appropriate. And then the logistic regression model is using a threefold validation set. And so it's taking kind of 30% of the data as a validation set and 60% fit, and it's kind of doing that 3 times. So in the next few slides, we'll get into exactly how that works. So in this slide, we'll be going over our logistic regression modeling process. And as stated before, we're starting with our full text values, which are simply comments. And we're looking to forecast our classes. So to do that, we take those text values and we break them into what's called bigrams, trigrams, unigrams, and n-grams, where kind of unigram is like single word, bigram being 2 words, and n-gram being a string of words. These kind of word features or sequences are really useful because you can kind of forecast using a vector. A computer can't really fit a model on text itself, so we need some sort of sequence of numbers or a vector to model any of our data. So the first step is find the most commonly occurring and unique words or sequence of words, as well as any additional engineered features that we managed to come up with. In this case, that's, is the comment have a lot of symbols? Is there a lot of capital letters? And does it seem like the person is using a lot of unique words, or kind of are they just using the same words over and over again? Once we have those kind of vectors, there are tools that we can use to extract those into numbers and relate kind of concepts to each other. So if we have a sequence of colors like red, blue, green, those might have kind of similar numerical vectors. From there, we normalize our data for kind of numerical stability, and then we can go ahead and fit our logistic regression model. In this case, we had about 30,000 features or X values, and to train to our 6 classes. Next up, we have our high-level overview of our neural network modeling process. Just like before, we have the problem of needing to take our text values and turn them into vectors or numerical vectors. In this case, we use a similar process where we kind of what's called tokenize the text or turn it into a numerical vector. We weight the terms for uniqueness and kind of commonly occurring, and we take those terms. In this case, we took about 30,000 terms, and 30,000 kind of words is a kind of a unique number because it represents the high end of what a standard human being would have for their vocabulary. We tested, whether using 10,000, 30,000, or 50,000 actually influenced the effectiveness of a neural network model, and in this case, we found that the middle value was pretty effective, although they didn't have drastically different results. Next, we choose a series of embedding vectors. Now, embedding vectors are really important because they allow the neural network to relate concepts to each other. This would kind of be like comparing colors for similarity, or comparing kind of audio measurements for how loud something is or how high pitched it might be. In this case, the computer has no background for what words are related to each other. So we can use embeddings, which are kind of large vocabularies of words where they've used a numerical process to create number vectors that are similar to each other for similar words. We use that as a kind of pre-training for our weights in our neural network, and then apply those embedding vectors onto the words that we actually extracted in our text. So from there, we can feed that embedded matrix into graded recurrent units, or GRUs. And this is kind of, from here, this is the architecture part. This is where we're kind of running multiple models to see which hyper-tuning parameters are going to be effective. This is what kind of helps the neural network really hone in on a set of sequences that works for it. So in this case, we tuned our dropout level. We chose an optimizer. We chose the Atom optimizer. And we, again, validated on 5% of the training data and fit models on batches of 64 observations. We kind of ran that until the performance of the model kind of levels out on the training set. So finally, we have our results. And this is the most important thing for us. If you really want to know whether your model can perform well, you need to look at whether it's kind of performing well on new data. And in this case, we can see that our accuracy levels are pretty high. So, if we're flagging something for toxicity, there's a strong chance in the training set and the test set that it is in fact toxic. For both models, they seem to be doing pretty well on both the training and the test set across metrics. And their performance from a Hamming loss perspective is pretty good. They're generally guessing and pretty well across toxicity levels. Our key problem seems to be there are many kind of positively toxic comments that aren't being flagged. And in this case, it has to do with symbols, kind of use of typos that aren't generally words or can't be tokenized the same way as other words would be, and other kind of modeling details. From our perspective, it seems as you look at the results, like the logistic regression model is kind of not able to generalize as well as the neural network. So we would expect the kind of forecasting power from the RNN to be higher and generalize better on new data. So in this case, we prefer to use that model. From our perspective, this modeling process is never really complete. And over time, we hope to improve it by having good handling for things like typo or synonymous swear words or things like that. So that concludes our results slides and our modeling process. Feel free to comment, and we would love to hear your feedback. Thank you.
These metrics are good for measuring the capabilities of the learning model. However, they might not be good in implementation. The moderators, in charge of enforcing the organization's policies, need a different set of metrics. The following key performance indicators allow moderators to quickly and effectively identify toxic comments and assess the level of their toxicity. The toxic comment indicator will return 1 or true if any of the labels for comment toxicity return higher than 50% likely. The toxicity index returns a value of 0 to 100 that reflects the degree to which the comment is highly toxic. This value is weighted, so we don't have to hide the effects of a comment that is highly obscene but not identity hate. A comment that qualifies as fully toxic, severely toxic, obscene, threatening, insulting, and contains identity hatred will score a 100% using this metric. Our dashboard leverages the toxic comment indicator and toxicity index KPIs to display information by user, by time, and by category of toxicity in order to measure trends and allow employees to enforce their company's harassment policy in a quick and effective manner. In some cases, we can set the automation of the organization's choosing that can lock or remove posts that exceed a toxicity level. This dashboard, however, enables frontline moderators and gives them all the information they need to quickly assess the overall toxicity and take quick action to improve user experience. In the top left, we see a pie chart that shows the overall ratio of toxic comments on the company's online platforms. We also display a timeline trend of this toxic comment indicator ratio over time to the users. In the bottom left, there's a detailed panel with comment text and information for the moderator to identify the highest toxicity index posts. A breakdown bar chart is provided to show the relationship of toxicity categories and their quantity. And the toxicity index is also provided at a user level, and this is displayed on the ribbon to the right side of the dashboard. Action can be taken to restrict these users from interacting on the website. For companies with a vast online presence, the cost benefit is clear. The cost of not implementing a solution to online harassment through toxic comments is the dehumanization of its customers, negative sentiment, and in some cases the threat of actual physical harm. There's a significant productivity benefit as well. The real-time tools enable employees to have all the information they need to take quick, effective action. Also, we preempt having to hire an army of moderators to manually search for toxic comments. Estimates from a high-volume website such as Twitter suggest that an average of nearly 30,000 moderators inspecting 12 comments a minute would be required to meet the demand of toxic comment filtering. Lastly, we want our online platforms to encourage civil dialogue in order to cultivate a better online experience for the customers of the organization. This leads to better customer sentiment and ultimately better customer loyalty. Through our work, we have made clear that applied analytics and machine learning can indeed identify toxic comments in a high-volume online platform. We have demonstrated the relationship between lower comment toxicity and better customer experience. Tools have been provided that can ease the manual intervention that is required to enforce a company's online policies, and this solution has real-world cost improvements and benefits. Ultimately, promoting safe places for people to interact online can have a good effect for brand loyalty and can allow organizations to better understand and serve their customers. This addresses all our prior business questions through a comprehensive analytical framework. Thank you again for your time, and happy commenting.